Okay, this is the second part of our course here at Krumhook. Krumhook, yeah, it's I'm a little like challenged with some of these names, but this was a course organized by Ivo Zimmerman, and these are pictures that we've taken in our tour here in Namibia. So this is a picture of us with Uwe overlooking his expanses there on his. Does he call it a station or a farm or what farm? Okay. So we climbed up onto the rocks here and we're looking at it. And as we drove in, then it was really interesting to see this on the road. There had been like enough rain to run down the road. And the rain doesn't, water doesn't like straight lines. So though the road was nice and level and everything, the water meandered. And all of the water molecules are in resonance to the pattern of the meander. So that it's got this oscillatory pattern. It's like snaking along, and it's with near geometrical precision that it's doing this. It's very interesting, the organization in water. So this is organized water running down the driveway as we came into Uwe's place. Now looking out from those rocks, then what I noticed is there's an area out there that looked different from all the rest. And you can see the more vibrant color in the vegetation that was above. It was on the uphill side of this ponding bank that Ivo designed to conserve the water. And this bank conserves and it spreads the water out over the land and allows the water to soak in. So instead of running off, then the water stays there and it soaks into the land, and we're seeing what happened as a result. So that was very interesting. This was before I actually got down in that area to see what was going on. Now this is what was going on. So on the uphill side of that ponding bank, this is what it looked like up close. But this is what it looked like on the other side of the ponding bank. And it's obvious that there's something more alive going on there where this water was captured and spread along that ponding bank. I think there's really something. Your observations of the broadest expanses are oftentimes telling you the most intimate details about how nature works. So you can see what's happening there, and then you can see what's happening there, and it's a big difference. So let's take another look at this and see what's happening within that ponding bank that's catching the water. Down here, underneath the grass, there is this diversity of creeping plants that's actually covering the surface of the soil. And when you cover the surface of the soil like this, then the soil becomes cooler and it emits less light and less warmth. And there's a significance to that we'll see. So one of the things that was happening is one of the plants that was covering the surface of the soil is a low-growing leguminous plant that the seed had to have been there in times past. And it was just waiting for the right conditions to come up and to cover the surface of the soil. And legumes draw oxygen into the soil. Rudolf Steiner in his agriculture lectures, described legumes as the lungs of the soil. And oxygen is the basis of acidity in chemistry, so the legumes in their root exudates are exuding acids, and the acidity around their roots is below a pH of 4. So what that does is the cations in the soil that are inactive and they're locked up are released by the acidity around the legume's roots. Now these are acids based on carbon and oxygen. So they aren't like, they don't have the kind of acidity that chloride, for instance, has. So they're milder acids, but they're still strong enough acids to get the pH down there below 4 and to unlock the cations in the soil, the lime complex. And until you do that, you can't get cell division to happen in fruiting plants like this wild watermelon. What it takes for cell division to occur in a fruit is it takes calcium and amino acids for the cell division to occur. So in areas where we had this wild watermelon that did not have the legume, there were no watermelons. It was only where we had the legume as a soil cover that it was releasing the calcium and promoting sufficient amino acid chemistry in the soil to achieve fruiting in this wild watermelon. Now, Ebo, who knows a lot more about the names of the legumes and grasses and other plants here in the environment in Namibia than I do, I'm actually an exotic myself. And I wouldn't have had any idea what the name of this legume was. But Ebo says this is Indigofera, and it is in the indigo family, or related to indigo, which is a wild legume where I am from in Georgia. So it's one of those things that would have its seed out there, and it's blossoming. See these little tiny orange blossoms? It's making lots and lots of seeds. So the next year, when there's a rain event that piles up water behind that ponding bank and sprouts this seed, then it's going to cover the soil again. So we're building up in this environment just because of having that ponding bank there. We're building up the conditions for plants that cover the surface of the earth. Here's another one. So the Indigofera wasn't the only one that's doing this. Nature provides, like, nature provides what we would call in aircraft maintenance, we would call it a fail-safe. Something that takes the place in case something doesn't work, then we've got a redundant system that fills in and works instead. So in aircraft, we had cable systems, and we had hydraulic systems, and we had electrical systems, and if one of them failed, surely one of the other ones would take its place. So, when you're in an aircraft, you can't just, when something fails, you can't pull over onto a cloud and fix it. You can do that on the highway maybe, but you can't do that with aircraft. And nature works more on that basis. So nature has got redundant systems that one of them will take the place if another one fails. And this is a lesson to think about if we're trying to eradicate a plant. We say, we don't want this plant. Maybe it has thorns on it. And we say, oh, I want to get rid of that plant. You ought to consider what's going to take its place. Because if you eradicate something that you don't want, how are you going to feel about it if something even worse that you want even less takes its place? So, but nature's going to find something to take its place. So that's a thought. Now, in the area where the water ponded and left mud behind, then it covered this particular legume with soil, with the clay that settled out on the leaves. But even though the water was muddy, this legume was thriving. Now you can see the indigo pharaoh up here in the left-hand upper corner of the picture, but it's filling in. The two of them together do more to cover the surface of the soil than the one by itself. Here's a different creeping soil legume, soil cover. And soil cover is a big, big deal. Here's another creeping plant, a helichrysum, that is covering the surface of the soil. Nature wants that kind of thing to happen. And if all we have is grasses in a pasture, you'll see the grasses stand straight up, but they don't cover the soil on the horizontal. So you have to have that diversity of plants, some of them that underneath the grass will cover the surface of the soil. If you were an animal living in that pasture, something tiny, like maybe a mite or a nematode or even an earthworm, and you didn't have anything but bare soil there, then you wouldn't have a very friendly habitat. So it's plants like this that allow the small tiny arthropods and nematodes and other types of soil animals to survive. And there's columboles, and there's springtails, and there's a wide variety. Many of those soil animals are so small you can't see them, but they wouldn't have a habitat if it weren't for this kind of soil cover. Now, in looking at this, this is Uwe, and this is me, and I'm looking down here, and we had clouds in the sky, and we were thinking about rain. And what's happening down here at the surface of the soil is this cover is cooling off the soil. The soil is not emitting warmth and light. This plant is using the warmth and light to make sugars through photosynthesis. So when we have bare soil, we're wasting our opportunity to build organic matter into our soil. And this organic matter, this is high protein because it's a legume. And it's full of minerals because it's a legume. And so this actually then, when it is digested by the soil's animal life, then it's high protein and it's really good tucker. That may be an Australian expression. Do you use that in South? Okay, well, tucker means what you put on the table and fork into your mouth. And and this is what's on the table there for those little soil animals. Here's another picture here that maybe doesn't do the best job of illustrating, but this kind of leaf actually catches moisture and it rolls off and soaks into the soil underneath this soil cover. And then when the sun comes out, then this is shading the soil, and what rolled off of it into the soil is still moist down there, and this is protecting it from evaporation. So what's happening when you have got this kind of cover on the soil is you're actually able to maximize the use of the moisture that falls out of the sky. Now here's an example of something I was telling Ivo about, and we were seeing as we were driving down the road, is in America, in the American Southwest, this is called a virga. This is a rain event that doesn't hit the surface of the soil. Now out in those environments there in New Mexico, there's a fellow from South Africa by the name of Alan Savory that has established an institute called Institute of Holistic Resource Management. And those farms, those grazing properties there that are practicing his concepts have almost 100% soil cover. The pastures are managed to maximize the cover on the soil. And on those ranches, then the virga is coming across the landscape, and where the soil is bare, it's a radiator. And I think if I hit this, it's gonna, whoops, okay, it didn't. Well, this is another example. In this area here, then the soil had cover, and it wasn't a radiator. All around, it was a radiator because there was bare soil. And that radiator is cooking the rainfall back up into the cloud, evaporating it back up into the cloud before it hits the ground. And what you would see on those properties where there's soil cover is at the fence line where the soil is covered, the rain hits the ground. Whereas on the other side of the fence, it's evaporating back up into the sky before hitting the ground. So that's something that happens. Something to think about. Tall grass does not cover the soil well, because what will happen as the grass gets tall and sits there, then it inhibits further growth of the grass. So the grass doesn't branch out, doesn't tiller out and spread and cover the surface of the soil. This is something that Alan Savory noted, is that when the grass, even if it's trampled, in fact, sometimes it's better if it's trampled rather than grazed, because it covers the surface of the soil, but it also lets the sunshine hit the crowns of grass. It lets the sunshine hit the crowns and stimulate those crowns to divide out into tillers that spread the soil's cover. And then you get denser grass cover. So when you have big tall grass get up there and stand there, it actually leaves more soil bare underneath it than if it was trampled down or grazed. So here we've got an example. This was in Uwe's inside an area where he has housing, and it had just been slashed, so it was mowed down, and you could feel the difference. This soil out here, just think about it, acts as a radiator. This soil in here is much cooler just because it was slashed and the soil surface is covered. Covering the soil surface makes a big difference in things. Here's another thing that we noticed. In the road, there was ant activity, and there was a trail of ants. Uwe was looking, these ants were trailing across the road here. And in some places, they just crossed the road. And the fact that there's life doing this, just imagine, for instance, this lighter color here is reflecting more light. So it's heating up the atmosphere more. This area here is absorbing more light, and it's cooling the atmosphere more. Now, the way ants work, ants are incredible. They couldn't write a book about it. They don't have an intellect as such. But man, they have an instinctive intelligence that does all the right things in most cases. So, and there's so many kinds of ants, and they do different kinds of jobs. So this kind of ant here was drilling down into the earth and pulling up like little balls of clay that were actually enriching the surface of the earth. Here was an example in his paddocks there where the water on a ponding bank had caused a termite uh, mound to collapse. And the termites, as you probably know, they dig down into the soil and they pull up soil and they aerate it and they make these channels. And when this termite mound collapsed, what that was a sinkhole to feed the water table. In short, it's an inlet for a spring further down the landscape. These are the kinds of things we need to think about, because if we as human beings manage the landscape, we can improve it. So, what I said earlier about farming in such a way that you grow food of the highest quality with what you've got, then these are important observations. Here was another thing. We were looking at this plant, and it's called Scelebos. Seckelbos, here locally. In some parts, I understand it's called Kalahari Christmas tree. This is the one that punctures tractor tires. And so what we were looking at there, in biodynamic agriculture, we have a technique for those plants which we have no way of otherwise like getting them out of the landscape and giving it over to some other plant. We have a technique called peppering. Now this plant makes a lot of seed, and if you collect its seed, then its seed has the boundaries that are essential for its reproduction. So if you burn it to an ash, you will destroy its boundaries. Remember what I said about life arises at boundaries? Well, this plant will have its unique characteristic boundaries in the seed coat. And when you burn that seed, then you put that ash out as to establish a pattern that will deny this plant any vitality where that ash has been applied. So you do that in successive years. It may not eradicate it in the first year or even the second, but if you keep applying that pepper, it's called a pepper because it looks like pepper. If you keep applying that pepper to an area, then you can eliminate that plant from it. That plant will fail to find any nourishment in that area. Here's an example of looking at a sort of a windrow or a contoured bush line is what Evo calls it. And it's a place that it attracts moisture, it attracts animal life, and it will act as a nurse-like cover to help grass establish that can slow down the flow of water across the landscape and filter out the erosion. So this is erosion control to foster a growth of grass in a line across the contour so that you arrest erosion. The whole idea is not to stop water. The idea is to slow down the water so that it soaks in. I've seen Australian farmers, I live in Australia, that they have said, oh no, I don't want to slow down the water because then I can't fill up my dams. And I've thought, wait a minute, where is the water going to do the most good? Is it going to do the most good in the dam, or is it going to do the most good in the soil? If the cows, in eating the vegetation, are eating dry vegetation, then they have to go to the dam to get a drink of water. But if they're eating lush vegetation, they don't. So where do you want your water? I would say you want your water in your soil. So slow down the water. You may not fill up your dam, but that's okay. You'll fill up your reservoir. And the soil is your reservoir, and that's where it does the most good. Will grow you the most grass. So from my perspective, then this practice is infinitely better than trying to dig a bunch of dams and channel all your water into the dam. It just, to me at least, it doesn't make sense to channel all my water into the dam when I could spread it out into the landscape and let it soak in. Then I wouldn't have to pump it from the dam to water my grass. I mean, think about it. Here's a thing. We were looking at these corn crickets, I guess they're called. And I was thinking, we have wild turkeys in the United States. And boy, they would love these things. They would get so fat on eating these crickets. There doesn't seem to be sufficient bird life in this particular environment here to actually capitalize on this kind of animal life. But maybe a flock of turkeys would. I happen to really like turkey because it's a bird that has a large amount of tryptophan in its amino acids. So when I eat turkey, like a Thanksgiving dinner in Georgia, then I have to go take a nap because all that tryptophan, see, tryptophan is one of the 3 amino acids that makes dopamine and serotonin in the brain. And those are the feel-good, chemicals in the brain's chemistry. And so I will feel so good with a belly full of turkey, and I'll go take a nap right after dinner. What you would find in countries where turkey is popular is that in the truck stops, the drivers never eat turkey before going on the road. Always eat turkey when they come in after a run. They may be very much stimulated by coffee or other substances to keep alert on the road. But when they come in and eat turkey, man, it's time for bed. So that's just something I was thinking of. I mean, this cricket can eat this high protein foliage on these legumes with thorns that elephants would balk at. So it's like this animal has the ability to eat those things that your zebras and springbok and all the rest of these things cannot eat. This one here is getting fat in this environment. Here was something that I noticed is the granadillas, which in Australia we call passion fruit. And they're very plump and shiny. It's always a good thing when you see this fruit and it's real fat and shiny. And that's a sign that the silica is working well in the soil around these plants. Silica, just think about it. Silica is what you make glass out of. Is glass shiny? Well, then you'd find that the shiny surfaces of this fruit are rich in silica. Silica is one of the most ignored elements in plant chemistry and animal chemistry for that matter. And it's of extreme importance because it is at the basis of cell walls, connective tissues, and transport vessels. Now, on another place, this was, I think, at Gabby's, and he had these grapefruits, and one of his grapefruit trees had been near death and was recovering. But the grapefruits on his grapefruit trees were not getting fat like normal grapefruits. They were sort of long and skinny, very skinny for a grapefruit. And that was a sign of the silica working very well, but the calcium being weak. Calcium works on the horizontal and it fills things out and makes them fat. Whereas silica works on the vertical and it elongates things. Silica is responsible for carrying calcium into the development of the fruit. So the silicon's working very well, and the skin of the grapefruit was without any flaw and without any uh, there's a sort of a smut that likes to grow on citrus skins, and it makes it look a little dirty and whatnot. But these grapefruit skins were absolutely pristine. So it was a good sign that the silica was working in this plant and that the calcium needed to catch up. This was an example. One of us pulled up a grass, and I was showing them what I call dreadlock roots or Bob Marley roots. These are Rastafarian roots. And you can see the soil adhesion on them. That soil adhesion zone is where the biological life of the soil is extremely rich. The actinomycetes would be forming a fuzz on the plant's roots, and the plant's root exudates would be feeding that, and the nitrogen fixation and protozoal digestion that feeds the plant would be going great guns in these Bob Marley roots. So that's something you want to look for in your grasses, in your pastures, your corn in your gardens, and this sort of stuff is you want to find Bob Marley roots. That's when it's really rocking. Now this was a sorghum plant we pulled up, and it had terrific roots. It had Bob Marley roots on steroids. But in pulling it up, then pulling it loose from the soil, it stripped them off of these roots and only held on to them close to the surface of the soil. So in here, it was clotted with soil adhesion to the roots. But when it was pulled up, then the roots got stripped of it, and we only had the inner core of the roots that stuck out. But it was really good. It was really good biology on that sorghum plant. Now this was a sorghum plant. Look at the color of the leaf, and it was in a maize field, and it was growing there as a weed. It was growing much better than the maize in this particular place. And that was because of those Bob Marley roots. We were also looking, this is Otto along with Ulf, and we were looking at his sun hemp and as a green manure, and looking at the soil that was around the roots of this plant. And then we were looking at the flowers, and I thought, gee, this ought to make a lot of honey, the sun hemp flowers. And we looked around for bees, and there were bees, even though the throat of this flower is pretty tight. Then the bees that were there were getting in there. But this would have been an opportunity for a beekeeper because there weren't enough bees in the environment. There probably are 3 or 4 different kinds of wild bees that would also access this plant, from bumblebees to other smaller wild bees I've seen in the area that do a similar job to the honeybees, but they're much shorter and they have a black abdomen. So, but in any event, this is an opportunity, this sun hemp is an opportunity for bees. Now we were looking at this, these were grown as a monocrop. So there was just sun hemp in one side and just lab in the other side. Now there was actually, see the purple flowers? There was actually wild sesame that was growing in here as a weed. But it was providing diversity. But monocropping does not provide synergy. Synergy is where you have 2 or more things growing together that produce a greater joint sum than if you grew them separately. So this was an example of where we need to invent new methods of agriculture. Now, I'm not giving a prescription that you do this or you do that. You need to think about it and try things and experiment because you are the pioneers of a new age in agriculture. And I might add, especially for the younger people in the room, that this, I believe, is the most exciting and most opportune time for someone young to get into agriculture as a career. And I don't mean getting into agriculture with the old war on nature sort of philosophy. I mean working with nature and finding out how nature works and how you can work with it to grow food of the highest quality with what you've got. Now we can see here where the seeding rate on the lab here was not achieving soil cover. This is one of the things that's imperative. Whatever you do, we need to achieve soil cover. Bare soil is a dead loss, and bare soil is dead. If you try to find life where the soil is bare, then you will have a challenge. If you look for life where the soil is covered, you won't have any trouble finding it. This was on the lab roots. Then we pulled one up. I think Otto pulled the root up, and it had this big nodule on it. And when you're looking at the nodules on legumes, then you need to look on the interior of the nodule to see if there's actually nitrogen fixation taking place there. And what we found in this nodule was inside it. Usually you're looking for a reddish color, but we found that the color was so intense it was black, and that intense black inside the nodules on this lab was a good indication of strong nitrogen fixation. It not only was black, it was juicy. You know, this is what you might call meaty, real high protein. In the sunflowers, they also were a monocrop. So you can see down the sunflower rows that there's bare soil. Now, the sunflower, once it gets up there pretty good, then the sunshine is only going to hit the surface of the soil where it penetrates through the leaves. So when it's near the horizon, it's not going to hit the surface of the soil. It's only when it's overhead. But still, there's no synergy in this sunflower field. So something needs to be found to produce that synergy in the sunflowers. It could be a legume, it could be a grass, or it could be both. And when we're planting crops and cover crops, then the sunflower could have been in a cover crop that was lower growing materials, lower growing plants. And the sunflower would have been the crop, and you'd run the header through and harvest the sunflowers, and you would have all that soil cover left behind. Then you could turn your cows in and graze it down and plant something that maintained the soil cover in the following season. So this is the kind of thinking that we need to get to in agriculture. Now I'm showing you these pictures not because this is what's ideal. I'm showing you these pictures to use your imagination on how to achieve a better result. Because what's going on in agriculture today throughout the whole world is we are wearing out our soils, losing our fertility, calling it income, and paying taxes on it. And that's a recipe for failure. So this is an example of what we need to improve on in agriculture. We would look at this sunflower field and think, gosh, that's a great crop of sunflowers. Looks like it, isn't it? Doesn't it? That's a great crop. But it's not building the soil as well as it needs to if we're going to really have a regenerative agriculture. Now, just in the wild, this is an example of what nature provides. This is a tiny plant, a euphorbia, that's trying to cover the soil. Nature has supplied this plant. Look, it grows in cracks in the sidewalks, this plant does. And it tries to cover the soil. It's tough. You know, anything that can grow in cracks in the sidewalk is pretty tough. And this is one of those plants that grows in cracks in the sidewalk. And you'll see people out there with their shovels and scrapes and whatnot trying to kill it. But I can assure you, on a hot summer day with bare feet, you'd rather walk on that one than the bare sidewalk. Because the bare sidewalk is contributing to global warming, and this plant is reducing global warming. This was sorghum, and we were looking out there at the sorghum. Where its leaves were dark green was a sign that the plant was getting enough magnesium in its leaves, because that dark green is chlorophyll. And chlorophyll requires magnesium. Well, you can't make good dark leaves on this kind of plant without magnesium uptake from the soil. And what provides magnesium uptake from the soil is actually sulfur. So think about it. Calcium sulfate is plaster, but magnesium sulfate is Epsom salts. Epsom salts dissolves into water and will be taken up by the plant. So if you look out across this landscape, you see where the sorghum is dark green, then it's got enough sulfur. And where the sorghum is lighter green, it's deficient in sulfur. Now sulfur also works, it brings oxygen into contact with the surfaces of all your soil particles. So when you get the sulfur in the proper levels in your soil crumbles. You look at this soil that was in that vicinity where the sorghum had enough sulfur and enough magnesium, and the soil crumbles. It's a beautiful crumb structure to the soil. So where you see a soil that's really gummy and tight, then what will open it up and get it to crumble is actually sulfur. Now, I don't mean to present sulfur as the final, only, and total solution to all the problems of existence, but I would recommend that modest amounts of sulfur should be applied to many of our soils to improve their structure. And where would you get sulfur? Well, sulfur is in the ocean. There's a lot of sulfur in the ocean. And there are microbes in the ocean that are giving off volatile sulfur compounds called sulfonates. And these compounds are critical in the nucleation of the rain. So where you will get that sulfur is where it rains. Sulfur is a free gift of the atmosphere. And James Lovelock, in his work on his Gaia hypothesis that the earth itself is a living organism, used that sulfur cycle from the oceans to the mountains and used that as an example of how the earth's circulation works as a living organism. So the earth is actually distributing the sulfur to the land, and what we have to do as farmers is to learn how to catch it and how to conserve it. Now you can see in this field here where this yellowy leaf in the sorghum is very deficient in sulfur. See that? The leaf is way too blonde. You can see off in the distance there where there's a darker green. But just to make sure you know what's happening, then when the sulfur isn't working, then the soil's particles do not give up what's on their surfaces. And then every other system in the plant, the boron, the silicon, the calcium, the nitrogen, fail to work properly because sulfur is not releasing what's on the surfaces of the soil particles. And then that stunts growth. So there you have another example. This is a weed here, just incidentally, which is capable of mobilizing sulfur. So this is the kind of weed that actually catches that sulfur that's in the rainfall and conserves it, builds it into the organic matter of the soil. So sometimes it's not such a good idea to get rid of all the weeds in your field because that's where the synergy happens. This is a plant that's actually catching and building sulfur into the soil's biological activity. Here's another weed. This tall, woody weed has a very tiny seed. Okay? So when it comes up where the nutrients are soluble. So where there's potassium and nitrate as salts, then this weed's seed will sprout and it will grow like topsy. If there is no nitrate or potash floating around in the salty portion of the soil, if those elements are poor in the soil, this weed may sprout, but it will not have what it needs because it's dependent on its nutrients to be soluble, whereas sorghum or maize or beans have big seeds that have a food package to get the microbes that release things like potash and fix nitrogen in the soil. So it's feeding the microbial life that will feed it backward in return. And this plant does not. This is nature's sort of mopper-upper plant that is there to catch loose nutrients before they leach away. So where you see these plants is actually where you see loose nutrients. This is a nitrate weed. You want to see another nitrate weed that's in this picture? Look at this one here. This one is called by various names in different places. It's called thornapple in some places. There's another name for it here. What's that name, Evo? It's a datura, and in Georgia it's called Jimson weed. In Arizona it's called loco weed because it has an alkaloid in it that is hallucinogenic. It's not very pleasant. It's not a fun thing to do. Malpita. Mad seeds. Well, they're mad seeds all right because they contain an alkaloid that if you ingest it, you will have a very very strange experience in it. Discontinuous reality is one of the experiences you will have. Discontinuous. It's hallucinogenic. And if cows eat it, then they may go loco. You know, loco is a Spanish word for mad. Okay? So it's called loco weed in the American Southwest. Okay? It's a nitrate weed. It comes up where there's been raw manure or there's been excess nitrates in the soil. It's a weed and it's telling you something. So both of these weeds, guess what's coming up? They're coming up where there's a surplus of nitrates in the soil. They're indicator weeds. Here is a weed, or a plant, that I really love because it's a really great silica plant. In Australia, we are harvesting the juice out of this plant and using it for a variety of things. I mean, it's great for shampoos. It's great for sunburn. It's uh, it's great for the skin. If you fill it out the meat, the jelly that's inside these leaves, then it's a great tonic for the intestines. Uh, yeah, aloe. I don't think it may not be aloe vera, but it's aloe. There seem to be, here in Namibia, there seem to be a variety of aloes, uh, and not necessarily aloe vera. But this one here can grow into, I believe it grows into a tall tree. And what, huh? It's got very sharp points on it. Oh, okay. Well, you'll see with a lot of silica plants that they have sharp edges. You know, maize is a silica plant, and if you're growing a really good crop of maize and you're out there pulling off the ears, you got to be careful or you'll slice the tar out of yourself. It's sharp. It's sharp as any paring knife. So in any event, this is a real rich silica plant. We were using it in Australia, about 5 liters of aloe vera juice to 1,000 liter shuttle, and it'll make you a compost tea that's rich in fungi, because fungi are dependent on the silica. See, so you use 5 liters, maybe of fish emulsion and 5 liters of aloe vera juice, and maybe a kilo of humic acid soluble humate powder, and you would grow a terrific silica rich fungal brew. So we use it for that. We also used it, we want to get the alkaloid that's in the leaf or in the circulatory system just under the leaf. It has veins, and if you cut the leaf off, it'll drip red like blood. It'll drip red out of those veins, and whatever's in there makes a really good deterrent for deer, rabbits, kangaroos, wallabies. I don't know what you have here in Namibia, but maybe it's warthogs or whatever. That they would get a taste of this if you used it as a foliar. They'd get a taste of that, and they would stop eating your cucumber vines and your bean vines. So they would get a taste of that in their mouth that they couldn't get out very easily, and they would be put off. So this plant can be used for a variety of things. It's a great plant, and it grows in the desert. So it's one of my all-time favorite plants. I've got a preference for silica plants.